Hello, everyone. So in this lecture, we're going to take a look at two things. First, some very basic relationships involving delta H, the enthalpy change of a reaction, which will lead into a really fun concept involving, once again, enthalpy change known as Hess's Law. So let's begin at the beginning here, relationships involving delta H. Now, in the very last lecture, which was on thermochemical equations, we found out that in a thermochemical equation, the delta H value at the end of that equation is very specific for the amounts of reactants and products in that equation as balanced. In other words, the delta H values are very, very specific to the quantities in the equation. So as an example, and we did several of these before, let's take something different. Let's suppose we have a reaction between iron 3 oxide and carbon monoxide, which is CO gas. And let's suppose this results in the formation of solid iron and carbon dioxide gas. Well, I can write this as a thermochemical equation by including the delta H value at the end. As it turns out, for this particular reaction, delta H is equal to -3 kilojoules. Okay. That negative, of course, means that this reaction is exothermic. It's exothermic by 23 kilojoules. Now, we're going to remember that this value, 23 kilojoules for delta H, is the heat released when very specific amounts of reactants and products are involved in the reaction. Specifically, that 23 kilojoules of heat is released when 1 mole of iron oxide reacts with 3 moles of carbon monoxide, forming 2 moles of iron and 3 moles of carbon dioxide. So once again, this quantity of heat here is specific to the stoichiometric quantities of the reactants and products as balanced. Okay, well, we know that delta H is an extensive property. In other words, if you change the amount of reactants, you change the amount of heat. Right? If there's more reactants, you're going to have more heat flowing. If there's less reactants reacting, there's less heat flowing. Well, as it turns out, since delta H is an extensive property, if the balancing coefficients in a chemical equation are changed, either by multiplying them or dividing them by some factor, well then delta H must be adjusted by the exact same factor. So, for example, let's suppose I rewrite that same equation above, but with different balancing coefficients. Let's suppose I multiply all of the balancing coefficients in that equation by 3. So now I have 3 Fe2O3s plus 9 COs to give us 6 irons and 9 carbon dioxides. Well, delta H for this reaction is not going to be the same as before. I've changed the quantities. And as it turns out, delta H is now going to be the original value, -23, multiplied by 3. And that's because in this equation, what did I do? I tripled all of the mole quantities in the original equation. And since I tripled them, well, delta H has to be likewise tripled by multiplying it by 3, or for this newly written equation, delta H is now -69 kilojoules. Or I could have gone in the other direction. I could have taken all of the original balancing coefficients and halved them. So in that case, I would instead have 1/2 Fe2O3, and I'm going back to the original equation, which is still in yellow, plus 3/2 CO, leading to the formation of just 1 Fe, plus 3/2 carbon dioxide. And well, once again, delta H will be different. Delta H for this new equation is going to be the old delta H value, but now since all of the original quantities were divided by 2, we have to do the same over here. And so in this case, let's just get a different color highlighter. What would I do without my pretty highlighters here? So 1/2 3/2, 1, and 3/2 now being the new balancing coefficients obtained by dividing by 2, well, delta H changes. We also divide it by 2, and that value is now, what is that, negative 11.5 kilojoules. All right, that seems to make sense. It's a fairly easy adjustment we can do if we change the balancing coefficients. Okay. Now, the second important thing that we can do to a thermochemical equation and the delta H values of a thermochemical equation is reverse the reaction. As it turns out, and it says it right here, this is relationship number 2. If a chemical reaction is reversed, then the sign of delta H is changed. Okay? In other words, delta H that is positive in one direction is negative in the other direction. And well, why? Well, if a reaction is exothermic and you change its direction, it now becomes endothermic. Exothermic, down the hill. Okay? But if you change the direction, now you're going up the hill. The hill hasn't changed its size. All it's changed is direction. So once again, if I'm just using the same original reaction in yellow at the top as my example, if I was to reverse the reaction and I started with iron and carbon dioxide as my reactants, and now my products are iron oxide, iron 3 oxide, and carbon monoxide, well, delta H for this reaction is no longer negative 23, it is now positive 23 kilojoules. So let's also highlight this particular change. Let's see, I need a new color. We're going to go with green. So over here, this was negative in the original, and it's now positive in the reversed reaction. Okay. So those are fairly simple basic relationships that we can easily use to manipulate thermochemical equations. Now, this is going to lead towards a really fun concept known as Hess's Law of heat summation. Okay. So enthalpy, H, is often described as a state function of a system. Now, other things are state functions of systems. Energy, for example, is also a state function of a system. But let's focus on enthalpy, and let's also talk about, well, what is a state function? What is a state function? Well, a state function is a property that depends on the present state of a system, not how the system arrived in that state. Okay. Another way to say this is that a state function is pathway independent. Pathway independent. Doesn't matter on the pathway it took to get to the present state of that system. Now, to illustrate what I mean by a state function, I'm going to use some non-chemistry examples to help you wrap your head around this concept. And my first example here will be, well, something that's hopefully in a good state. Let's think about, say, your bank balance, your bank account. Okay. So let's suppose you go to the ATM machine. Maybe you want to withdraw some money. Maybe you just want to check what your balance is. And you find out when you check your bank balance that, oh, I don't know, that your current bank balance is $200. Okay. Now, this represents the present state of your bank balance. And it's all that matters in that moment in time. The moment in time that you check your bank balance, its present state is all that matters. Now, what does not matter is how you ended up with $200 in your bank account. So there are many different ways you could have ended up with $200 in your bank account. So, for example, you could have deposited $800, and then you could have withdrawn $500, and then you could have withdrawn another $100, and voila, you would end up with the $200. That is one possible pathway to have ended up with $200. Or, well, like I said, there are many different pathways. Maybe instead you deposited $50, deposited another $75, deposited another Whoops, that's not quite right there. That should be a plus sign. Let's make it a little neater here so you can follow along. So I said we deposited another $75, and then we deposited another $125, and maybe that's how you ended up with $200 in your bank account. The point is, it doesn't matter how you got there. All that matters is its present state. It's a state function. Well, let's explore another non-chemistry example of a state function, but one that will get us a little bit closer to, well, where we're going, which is enthalpy. So another good example is an altitude change. Altitude change. Okay. So let's suppose you're a mountain climber. I don't know. And let's suppose you're going to be climbing this mountain. Okay. And your goal is to get from here, which is your initial position, to here, up here. I don't know, maybe there's a really good view up there. I don't know, maybe they make special coffees there. That's what you want to do. Okay. Now, obviously, as you climb the mountain, there are many different pathways that you could take. So, for example, maybe, I don't know, maybe you're into climbing straight up sheer rock faces. And you're going to go all the way to the top and maybe say, hello, world, take a few selfies, and then you're going to get to here. So that's one possible pathway you could take. I'm going to call that pathway A. Okay? But maybe there's another pathway you could take. Maybe there is some steps that are in the wall, the mountain, and you could go up this way. This way would be pathway B. Or maybe you're like me and you're like, oh my God, I can't get up that mountain. That's too hard. And so maybe you do a sort of zigzag thing as you cut back and forth to get there. All right, this could be a pathway C. All different pathways to get from your initial position to your final position. Now, all right, each pathway, all right, is entirely different from the other. But what does not change, regardless of whether you went on pathway A or pathway B or pathway C, is this change right here, which is your change in altitude. All right, this stays the same because it's the difference between your initial position on the ground and your final position on top of the hill. So this is a state function. Now, I should note that what is not a state function is the distance you travel. The distance you travel does depend on the pathway you took. All right, based on my drawing here, I would say that C is the greatest distance because we're zigging and zagging back and forth, and B is probably the shortest distance. So the pathway you take does affect your distance, but not your change in altitude. Okay, well, now that we have a better sense of what state function is all about, pathway independent function, well, how does that relate? Well, since enthalpy is in fact a state function, well, it means that the enthalpy change, delta H, going from a particular set of reactants to a particular set of products is also pathway independent. When we start with a set of reactants, it's like our initial position on the ground. And when we end with a particular set of products, it's like getting to the top of that mountain. And as it turns out, the conversion of those reactants into a set of products is also pathway independent. Now, what does this mean? Well, there's the take-home message. It means that delta H for the overall process, and I'm going to underline this, is going to be the same whether that reaction occurs in one step or in a series of steps. Okay, let's illustrate that with an example. So let's suppose in our example, all right, we are going to have a reaction take place between nitrogen gas and oxygen gas to form the only product, nitrogen dioxide. So N2 and O2 react to form NO2 gas. That's the reaction. Okay. Now, this is our set of reactants. Oops, that's not a very good line here. And here, let's try that again. So there's N2 and O2 gases reacting to form NO2. So we're starting with these two species as our particular set of reactants. And the product that we want to make, the particular product, is NO2. Now, this reaction could be envisioned as taking place in one step. Now, if this reaction occurs in one step, well, the reaction would be N2 gas plus O2 gas in one step, giving us what we're after, which is NO2 gas. Turns out that this is not balanced as is. We're going to need a 2 here and a 2 here to balance it. So that's a direct conversion of the reactants to products. And it turns out delta H for this reaction is positive 68 kilojoules. Now I could sketch this reaction in an enthalpy diagram. So, whoops, I didn't want it to float away just yet. So this is an endothermic reaction, and that means that we're starting with reactants with low, oh, that's a terrible line. Let's try again. So we have our reactants that have low enthalpy, and that would be nitrogen and 2 oxygens are the 2 reactants we're starting with. And, well, when these low energy reactants, this is our potential energy axis, react, they end up with higher enthalpy. This is an uphill picture where we now end up with, I'm going to need a little more room, I think, for this diagram here. So let's put it over here. We're now going to end up with 2 NO2s. And this represents the reaction as an enthalpy diagram. I'm going to clean this up just a choops. There we go. That's a little better. 2NO2 here. So that's the one-step process going up the hill, and delta H is positive 68 kilojoules. Let's note that this axis indicates the reaction direction. Okay. Now, this reaction could also occur in 2 steps, in a series of steps. Now, to envision this reaction taking place in 2 steps, well, perhaps nitrogen reacts with oxygen to form not nitrogen dioxide, but nitrogen monoxide. And this is actually not balanced. So, oh, it is balanced. That's 1, that's 1, that's 2. Well, it turns out that delta H for this reaction is positive 180 kilojoules. Now, that's the first step. Let's call that step A. Okay. Now, in the second step, these NOs that were formed in the first step can now react with another oxygen. And when they react with another oxygen, well, they then form the product that we're really after, where that product is 2 NO2s. So let's call this step B. And I'm just going to clean this up a little bit here. Let's move this out of the way. This is our gas in the first step. Delta H for this step was positive 180 kilojoules. I'm just trying to make it a little easier for you to read and follow along. Turns out for the second step here, delta H is equal to negative 112 kilojoules. Well, let's add these steps to my picture. So we're still starting here with reactants nitrogen and oxygen. And I still want to end up here with nitrogen dioxide. But now we're going to take a different series of steps. If step A occurs, nitrogen reacts with just 1 out of those 2 oxygens. So I've got 2 oxygens right here. Let's suppose nitrogen reacts with just 1 of them to form 2 NOs. Now, That's also an endothermic reaction, positive 180. That's a lot more endothermic than the positive 68. That's almost 3 times as endothermic. And so that reaction is going to go whoop, all the way up here. And I'm going to make this step blue. Okay. So this here is step A. And when step A occurs, well, what do we end up with up here as a result of step A? Well, we now have two NOs. But since we only used one out of the two oxygens, we still have an oxygen left. And well, now the two NOs and the oxygen can react together in step B. Note that step B is exothermic. So instead of going up the hill, we're coming down the hill. And here we go. Boom, 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 boom. Oops, that was not a very good straight line, but you get the idea. We come down the hill for step B, and where do we end? We still end up with two NO2s, just what we wanted to end up with. Now, the overall enthalpy change is the same whether we did the one-step approach or we did the two-step approach. The overall enthalpy change is the difference between the potential energies of the original reactants and the original products. It's this change here. So this is the same. All right, whether it's one step or two steps. All right, that difference. So this is, of course, the overall delta H, all right, for the overall reaction that's taken place. Okay, well, let's now explore this just a little bit more. Note that that picture looks a lot like this picture over here with our altitude change. So I just wanted to note the similarity there. Now, at this point, we can actually state what Hess's law actually is. So Hess's law says that if a chemical reaction can be expressed as the sum of a series of steps, well, ultimately, delta H for that reaction is the sum of the delta H values for each of the individual steps. Okay, let's just use the previous example to express what's going on here. Okay, so we had a reaction step A. And in step A, nitrogen was reacting with oxygen to form two NOs. And delta H for this step, we could call it delta HA, had a value of positive 180 kilojoules. Then, all right, a second step occurred. And in that second step, all right, two NO gases reacted with an extra oxygen and then produced two NO2s. And delta H for this step, let's call it delta HB, equals negative 112 kilojoules. Okay. Well, I can take these two steps and combine them together. We can add them together. Now, how do we add reactions together? Well, anything that's on the reactant side in both reactions stays on the reactant side. Anything on the product side for both reactions stays on the product side, but anything on opposite sides gets canceled out. So these two NOs get canceled with these two NOs. So what's left? Well, if I combine these two equations together, I'm now going to get N2 gas plus, well, I've got an oxygen here and another oxygen here, so that's two O2s. And on the product side, all that's left is two NO2s. In other words, the two steps added up to the net reaction, which is right here. Here's the net reaction where we started with N2 and two O2s and ended with the two NO2s. So this is the net reaction. Now, delta H for this reaction, all right, can be obtained by simply adding the delta H values for each step. So it's equal to delta HA plus delta HB. or delta HA positive 180 plus delta HB negative 112, which equals positive 68 kilojoules, which, by the way, is exactly what I said delta H was for the one-step reaction right here. So if we can break a reaction into individual steps by adding the delta H values for the individual steps, we can get delta H for the net overall reaction. Okay, well, that's kind of useful. It's a useful way to obtain delta H values for reactions from the delta H values of other reactions. So let's now take a look and see how to apply that by doing a couple of examples. Hess's Law problems are super fun, so you'll have fun, hopefully, when you do them in the homework. So let's take a look at our in-class example number 10. It says, given the following data, and we're given two reactions. Reaction A is between copper and oxygen to give copper oxide, and we have a delta H value. And reaction B is the reaction between nitrogen and oxygen to give nitrogen dioxide and another delta H value. Now, we don't want delta H values for either of these two reactions. Instead, our goal is to figure out delta H for this reaction, where that reaction is the reaction between copper and nitrogen dioxide to form copper oxide and nitrogen. Okay, so what are we going to do here? Well, the two equations that we're given, A and B, cannot be added together to give this reaction down here. Let's call this reaction the net reaction here. It's what we're after. It's what we want. Okay. Now, we can see that reaction A contains some of the things we want, and reaction B contains some of the things we want. Well, let's start with the things that we want. For example, reaction A has copper in it, and copper is something that we want. Copper appears right here in the net equation. Reaction A also contains copper oxide. Now, copper oxide also appears in the equation that we want right here. Okay. Notice that in the net equation, all right, copper is a reactant and copper oxide is a product. In reaction A, step A, copper is a reactant and copper oxide is a product, meaning that copper and copper oxide in step A are on the correct sides. They're on the correct sides, which is good. We like when things are on the correct side. But we do have a quantitative problem. When we look at the net equation, well, the net equation reveals that we need 4 coppers and 4 copper oxides. In reaction A, we have 1 copper and 1 copper oxide. And so to get the numbers right, we're going to have to multiply this equation by 4. Okay, well, if we multiply this equation by 4, all right, what does it become? So let's rewrite that equation multiplied by 4. So now we're going to have 4 coppers plus 4 times a half, 2 oxygens, yielding 4 copper oxides. Now, if I multiply that equation by 4, delta H is going to change for that equation. It too has to get multiplied by 4. So we have negative 157 times 4, and I actually haven't worked this out yet, so let's do it together, negative 628. Okay, so that's what I did to step A. Now, step B also contains some species that I'm really interested in. Step B contains nitrogen. I want nitrogen to appear in my final equation. Here's nitrogen in my final equation. Step B also has nitrogen dioxide in it. And I also want nitrogen dioxide to appear in my final balanced equation. But note that they're on the wrong side in step B. I want nitrogen dioxide to be a reactant, not a product. And I want nitrogen to be a product, not a reactant. So what am I going to do to this step? I'm going to have to reverse it. Okay. in addition to reversing it, I'm also going to have to pay attention to quantities. Note that in the net equation, I want 2 nitrogen dioxides, but I only have 1 in step B. So what do I have to do here? I have to multiply step B by 2. So we're going to reverse it and multiply it by 2. Now when I do that, what do we end up with? Well, I'm going to end up with 2 NO2s. And, well, 2 times a half, I'm now going to have 1 nitrogen. And 2 times 1, 2 oxygens. So that's what happened when I reversed and multiplied by 2 reaction B. Now, delta H again changes. Okay. So that positive value gets flipped to a negative value. So it's now negative 33 because sign changes. And we have to multiply this by 2, so negative 66 kilojoules. Well, now that we have made these changes, I can add these equations together. And when we add these equations, what do we end up with? Well, we end up with the net reaction. Let's see how. Well, what's going to cancel out here are the 2 oxygens here and the 2 oxygens here. Everything else stays, and so what we end up with are 4 coppers plus 2 NO2s, yielding 4 copper oxides and 1 nitrogen gas. In other words, we now have the target equation, the net equation that we were after. And if I want to get delta H for this reaction, well, I just add the delta H values above. It's going to be negative 628 plus negative 66, or in this case, negative 694 kilojoules is the delta H value for the overall net reaction that we were after. So let's just circle this as our final answer. So notice what I did. I took a look at the steps provided. So these are the steps. And I analyzed the steps to see how they needed to be manipulated so that I could then combine them together to give me the net equation that I was looking for. Okay, so it's kind of like working out a puzzle. And so these problems tend to be, well, at least to me, they tend to be quite fun, and I think most students actually enjoy doing these types of problems. Let's do one more like this. So this is number 11 in the in-class examples, and it's the same idea. We're given several steps, all right, reaction A, B, C, and D, which I won't read out aloud, with their delta H values for each particular reaction A, B, C, and D, but we don't want those delta H values. We want delta H for this reaction at the bottom, which is the reaction between boron and hydrogen to give us diboron hexahydride. That's what we're after here. So once again, this is the net equation that we are trying to combine all the steps together to get this net equation. That's our goal here. So let's once again go through each of the steps and think about what do they have that we want. So does the first equation have anything that we want in it? And the answer is yes. The first equation has boron in it. And, well, boron is in the net equation. Let's note that boron is on the reactant side in step A. It's also on the reactant side in the net equation, which means we're not going to need to reverse that equation. Then we're going to take a look at quantity. And we're going to see that this equation contains 2 borons, which is precisely the amount of boron I need. Which means step A does not need to be changed. So this step is okay to go. So I'm going to rewrite that step down here. So we've got 2 borons plus 3/2 oxygen, yielding B2O3, and the delta H value is exactly as it was before, negative 1273 kilojoules. Well, let's take a look at reaction B and ask ourselves again the question, does reaction B have anything we want in it? And the answer is yes. So reaction B has B2H6 in it. And well, here's B2H6 in the final equation here. And one thing we're going to notice is that in step B, it's on the wrong side of the equation. We want B2H6 to be on the product side in our net target equation, which means we are going to have to reverse this reaction. We're going to reverse it. How about quantity? Well, the quantities look good. I see 1 mole of B2H6 in step B, and there's also 1 mole of B2H6 in the net target equation. So that should be all. That's all we need to do is reverse this equation. So let's rewrite that equation in reversed form. So I'm going to have B2O3 solid plus 3H2O gas yielding B2H6 gas plus 3 O2s gas. And the only thing we did was reverse this reaction, and so the negative becomes a positive 2035 kilojoules. Okay, now let's take a look at the third step, reaction C. And again, same question. What does reaction C have in it that we are possibly interested in? And well, reaction C contains hydrogen. And we want hydrogen in our final equation. So in step C, hydrogen is a reactant. In the net equation, hydrogen is also a reactant. So that's great. We don't have to reverse the equation, but we're going to notice that there are 3 moles of hydrogen in the net equation. We only have 1 in step C, so we're going to have to multiply this by 3. So let's multiply step C by 3, and that's going to give us 3H2 gas plus 3 times a half, 3 halves O2 gas, yielding on the product side 3 times H2O, 3 H2O liquid. And delta H is going to be adjusted from negative 286 by multiplying by 3. And, well, I haven't done that yet. 286 times 3, negative 5, 858. 858 kilojoules over here. Okay. Now we have a step D, and right now it might not be immediately obvious how step D is going to help us out. So when you're not sure how a step is going to help you out, I'm just cleaning this up a little bit. It's important to then take stock of what we've done so far. Let's suppose I just took these 3 steps that I've rewritten and started to get rid of things. Well, what can I cancel out right now? Well, this B2O3 cancels with this B2O3. They're gone. Okay. What else can we cancel out? Okay. Well, you might be tempted to tell me that we can cancel out the waters. So when we look at this here, let's get a different color. Here we go. I see 3 H2Os on the reactant side here, and I see 3 H2Os on the product side here, but we do have to be very careful, and that's because one is a gas and one is a liquid, and they can't be canceled out this way. So we can't cancel out the waters just yet. Okay, but what we can cancel out are the oxygens. Notice in the first equation, I have 3 halves oxygen. And I have another 3 halves oxygen on the reactant side in the third step. Well, 3 halves plus 3 halves is 3. So that means I have a total of 3 oxygens on the reactant side, which can cancel out with these 3 oxygens on the product side. So be careful with fractions. They're going to be important. So now at this point, we've gotten rid of everything we didn't want except these water molecules. Let's just fix that over here. And that's because we cannot cancel a gas with a liquid. And hopefully that is now going to reveal the purpose of step D. Step D is there to help us cancel out liquid water and gaseous water. So let's take a look at step D. And do we want to keep step D in the direction it is in, or do we want to reverse it? Well, note that the gas in step D is on the product side. And over here, the gas in step D is on the reactant side, which is good. We want to keep it that way if we want them to cancel out. And so we're not going to reverse this equation. There, I keep doing this to this poor water molecule. Let's write it back in. So we're not going to change the direction of step D, but we do need to change the quantities because I need to cancel out 3 gaseous waters and 3 liquid waters, which means, drum roll please, we're going to multiply this particular equation. We need another color here. Let's multiply this equation by 3. We're going to multiply this by 3. And when I do that, let's now rewrite that equation here. We're going to end up with 3 H2O liquids yielding 3 H2O gas. And delta H is now going to be positive 44 times 3, since that's all we did over here, or positive, and I'm plugging and chugging madly on my calculator, positive 132 kilojoules. Okay, well now I can take all of these manipulated equations and add them together. We've already seen the B2O3s cancel out, the oxygens cancel out. Well, what can we cancel out now? Well, now these 3 gaseous waters cancel with these 3 gaseous waters. And these 3 liquid waters cancel with these 3 liquid waters. And so what do we end up with? Well, what we end up with here are 2 borons. We end up with 3 hydrogens. And we end up with the B2H6 product, just like in our net equation. And so let's just write that down here. I'll tell you, it's nice to have all these fun colors when I'm doing these types of problems. So we're going to end up with 2 borons plus 3 hydrogens yielding B2H6 gas. This is also a gas here. And delta H for this overall reaction is the sum of all of these manipulated delta H values. So negative 1273 plus positive 2035 plus negative 858 plus positive 132. In the end, there can be only one. So let's just plug and chug this out. And please check my work. I end up getting a value of positive 36 as the enthalpy change for that target net reaction. Okay, like I said, it's like solving a puzzle. And the way you get good at solving puzzles is to practice solving a lot of them. So go forth, practice your Hess Law problems, and conquer them, because it is rather fun. They're not that strenuous once you get the main idea here, which hopefully you now do. Okay, great. Take care, and I'll be talking to you again very soon in my next lecture. Bye-bye now.